Good day, folks. Welcome to Bright Mind Academy, where we bring brilliance to every lesson. So, as promised from the previous video, in this video we're going to be looking at percentage purity as well as percentage yield. Now, I need you to remember all the steps for limiting reagent because we're going to continue where we left off. Okay, yes. All right, let's look first on percentage purity. We will look at percentage yield. Okay, yes. So, what exactly is percentage purity? I want you to take this example. It's basically simple. It's just you understanding this. I might have uh what example can I use? I might have a share like that, okay, and say maybe I have okay, what I want to make a proper example that is gonna be a good and understandable, okay. So okay, let's say now we are having uh send here, okay. We are having send, we are having send, we are having send. This is a send, okay. But now in this send we are having gravels, little gravels there, okay, gravels there. So these gravels cause us to have impure what, impure sand. Why? Because the pure, okay, the impure sand consists of the what, of the pure sand plus the gravels, okay, majwe. The gravels, okay, little mini stones. I don't know what you call them, mini stones. We say they are gravels. So what we need to do here, it is to determine the percentage purity by saying what? When you want to calculate percentage purity, you will be given the impure sample, okay? So you need to say percentage purity is equal to uh, maybe mass of the pure divided by mass of the impure, okay, and then you multiply that by 100. So this is basically that they will give you the impure, and then you need to use your ratio there in a chemical reaction, okay, to find the what, the mass of the pure, and then do this calculation. So basically we're gonna use stoichiometric calculations, okay. We're gonna need stoichiometric calculations, and then on, remember stoichiometric calculation has 1, 2, 3 steps. So on this one you're gonna just add the last step, which is now adding percentage purity, okay. Yes, so I think you are ready to have an example. And another thing, I cannot find the number of moles of the impure, okay, unless they told me to calculate the number of moles of the impure. But if they want percentage purity, I cannot calculate the mass, what, the number of moles of the impure, or rather use stoichiometric calculations involving the impure. Okay, let me have an example. Where is that example that I have? Let me fetch it quickly. Uh, let me quickly fetch that. Okay, now let's consider an example that I have here. Okay, it says what? It says an impure sample of calcium carbonate. So they are already telling you that calcium carbonate is an impure, contains a calcium sulfate as an impurity. Okay, it contains calcium sulfate as an impurity. When excess hydrochloric acid was added to 6 grams of the sample. So it means now the impure mass, can you see that when excess hydrochloric acid was added to 6 grams of the sample, which sample? The sample of impure calcium carbonate. So I already have what? Impure calcium carbonate. Impure calcium carbonate, it is how much? 6 grams. Okay. Then they tell me that 12,000, sorry, 12,000 1,200 centimeter cubed of gas was produced, measured at STP. Okay, so I have a 1.2 centimeter cubed of gas was measured at STP. So which gas is that? Carbon dioxide. Okay, then they say to me, calculate the percentage purity of the calcium carbonate sample. So I want you to understand this. I know that here, this it is impure, right? right? And I cannot use this one because this one is in excess. Actually, let me not talk about this one so that you don't get confused. This one, it is an impure, right? So when this impure reacts, okay, when this impure reacts with HCl, only the pure, only the pure will react with HCl to produce what? All these three. Okay, so only the pure will will react with what? With HCl, because the reaction will occur when calcium carbonate reacts with what? With HCl. So it means now this impurity of calcium sulfate will not react. Okay, so what do I mean by that? So it means now I know that it is going to form this much. I know the volume of this one. It is 1,200 centimeter cubed, which is the same as 1.2 decimeter cubed divided by 1,000. And I know that at STP, so it means I also know the molar volume. Okay, so I can get the number of moles of the one that I know. Remember stoichiometry, initially it says calculate the number of moles of the known, which is what in this case, carbon dioxide. Okay, so I can get number of moles of carbon dioxide and then use the mole ratio between this one and the one that I want. Which one is that? Calcium carbonate. Okay, and the number of moles that I'm gonna get, it is the pure. Okay, the one that I'm gonna get, it is the what? The pure. Then I'll get the mass of the pure and then do the mole ratio. I mean, calculate the percentage purity. Step one, let me find the number of moles of the one that I know, which is carbon dioxide. Using which formula? V divided by Vm, because now I have volume as well as it is produced at where? At STP. It's going to be 1.2 divided by 22.4. How much do I get? 1.2 divided by 22.4. I get something like 0.053. 5357 moles. Remember, this is not the final answer you convert to for this mark. I'm done with step one of stoichiometric calculation. Remember, I said for percentage purity, you need 4 steps. The 3 steps of stoichiometric calculation, as well as the last step where you calculate the purity. Okay. Then now I need to use what? The mole ratio between what? The mole ratio between calcium carbonate as well as what? As CO2. Okay, the mole ratio between calcium carbonate and CO2, it is 1 is to 1. So it means now if the ratio is 1 is to 1, it means the number of moles of carbon dioxide, it is equal to the number of calcium carbonate. Okay, I'm going to calculate the calcium carbonate. The one that I've just calculated here, it is the number of moles that are pure. Okay, that are pure, which is equal to 0.05357 what? Moles. Okay, then step number 2 is complete. Step number 3. Step number 3 is what? If I calculate whatever. What is it? That the mass. Okay, remember, I still have the mass of the impure as 6 grams. So I need to calculate the mass of the pure using number of moles is equal to mass divided by molar mass. Number of moles, it is 0.05357. All right, 5357, it is equal to mass divided by, what is my molar mass? Molar mass of what? Molar mass of the calcium carbonate. It is going to be equal to how much? 40. It's 100 actually, the answer here. I'm just showing you. 40 plus carbonate is 12 plus 3 into 16. Then I have something like 48 plus 12, it is 60 plus 40, it is 100. Then I get in actual fact that the mass of calcium carbonate, since when I used the pure number of moles, it means this mass is going to be what? Pure is going to be how much? 0.05357 multiplied by 100. It gives me something like 5.357 grams. I'm done with stoichiometric calculations. But now the question said what? Calculate the percentage purity of calcium carbonate. Simple. Therefore, I need the step number 4 that says for me to calculate percentage purity, I need what? I need to say mass of the pure divide the what? The mass of the impure multiply by 100. And obviously, it makes sense that the mass of the pure is less, okay? Because if I'm having an impure, if this whole part it is impure, it means some portion it is the pure, so it's gonna be less. Then when I do my mathematics thereof, I get 5,357 divided by what is the mass of the impure? It is 6 multiplied by 100, and then let me see how much do I get the percentage thereof. I get something like 89,28 what grams. So percent. This is percentage purity, percent. Can you see how easy it is? Let me see if there's another question that percentage purity. No. Okay. So this is just the only question that I got for percentage purity. But when you do the calculations, we will see it is basically like this. Okay, always like this. Now let's look at percentage purity. So percentage yield. On the percentage yield, what do we do? What exactly is percentage yield? So basically, I want you to take this example, okay? Assume that you are in a lab, okay? When you are in a lab, you are planning to go to mining, okay? When you go to mining, you have to do your calculations, okay? What we do in class, we call it a theory, okay? So it means you need to do theoretical calculations, okay? The theoretical calculations says that when you go to the mine, you're gonna get 50 grams of gold, okay? This is the theoretical, okay? The one that you calculate. But when you go there and do practical, which is the actual one that is gonna get, that is produced. The actual, it is the one that is actually produced, okay? Or the one that you actually get from the mine, okay? When you go to the mine, you maybe get something like 42 grams of, of gold. So how do we calculate the percentage yield? The percentage yield is calculated as percentage yield. It is going to be the actual yield, okay? The one that you get or the one that is produced divide by the theoretical yield. For now, we are going to be given, actually, we are going to be given the actual yield because it's not the one that we can physically go and do it again. So they will give us that actual yield. But now we will do what? Theoretical, because remember, theoretical is what we can do, calculate again. We can calculate it, and then the scientists will go back and tell us exactly how much they got, or the miners, okay? Not the miners as in like subtraction, the miners, people who mine, okay? Then this is the formula you're going to use for percentage what yield. It's not that difficult. It's the same as percentage purity. If you were to take it like that, it's the same. Okay, this is actual yield. And then this is theoretical what? Yield. Okay, yes. Then what happens is, let's have an example. That's what happens. Okay, let me quickly fetch an example here of what we might have. So let's encounter a problem involving the percentage yield. So percentage yield, the steps are the same as the ones that you use to calculate percentage purity. Okay, step one, use the known number of moles of the known, get the number of moles of the known. Step two, use the mole ratio between the known and the unknown. Step three, in this case, the unknown will be the percentage. Okay, never mind. Step two, use the number of moles between the known and the unknown. Step three, get the what? The mass or whatever of the what? Of the theoretical. And then step number four, calculate percentage yield. Let's see. Talking won't help. 123, sorry, I don't know how to call numbers. 128 of sulfur dioxide was reacted with oxygen to produce sulfur dioxide, okay? The reaction, it is like that. Is it balanced? Yes. They tell us that 140 grams of sulfur dioxide was produced. So it tells me that sulfur dioxide, it is a what? Sulfur dioxide it is a what? It is the, remember it is produced. So this is the actual yield. The one that is produced, it is the what? The actual yield. Okay. So it means now we need to calculate what? So this is the actual yield. So it means now we need to what? To calculate a theoretical yield. We need to calculate what? Theoretical yield of what? Of SO3. Okay. Now I'm gonna use the first ratio. Now I'm told that sulfur dioxide SO2 was reacted. So I'm gonna use sulfur dioxide rather to get what number of moles of the node, because I have the mass of it, I can get molar mass of it, I can get number of moles. So it's gonna be number of moles of sulfur dioxide. It is equal to mass divided by molar mass. When our mass is 128 divided by what is molar mass of sulfur dioxide. Sulfite is 32 plus 2 into 16. Then I get something like 32 plus 32, which is 64. And then if I do my mathematics very well, I get two moles. Okay. Then, but remember, I need what? Number of moles of sulfur trioxide. Okay. So I'm gonna say between the mole ratio between sulfur dioxide and sulfur trioxide, it is what? 2:2. Can you see that? The ratio it is 2:2. That can be simplified to 1:1. Therefore, remember, if the ratio is 1:1, it means number of moles of SO2, it is equal to the what? Number of moles of SO3, which is in real fact become what? 2 moles. Okay. And if that's the case, therefore, I can calculate the mass of the what? Of sulfur trioxide. So I can say number of moles. This is step 3. Mass divided by molar mass. Number of moles, it is 2. What is the mass? I do not know. I want to calculate it. Molar mass of sulfur trioxide is going to be 32 plus 3 into 16. Then I get 48 plus this. I think it's something like 70. No, 80. Let's see, 32 plus 3 into 16, 80. Okay, 8. Then mass of SO3, theoretical, it is equal to how much? 160 grams. Okay, 160 grams. Remember the actual yield, the one that you actually get or produce, it is going to be less than the one that you calculate, because when you calculate, we assume that there are no errors. Okay, but during the production of something, there might be errors. So for percentage yield, it is equal to actual yield divided by theoretical yield multiply by 100. I think I forgot to mention multiply by 100 here. Remember, every time when you want percentage, you just multiply by 100. Then how much do I get? I still need to do this. Remember, the actual was how much? 140. The one that was produced, the one that we calculate on it is how much? 160. And then I multiply that by 100. And then I get something like 140 divided by 160. Then it gives me something like 87.5%. Is that clear? I think so. I want to believe so. Then I have at least one example here regarding percentage yield. Okay. We might need to do it on its page. So I'm told that calcium carbide is produced industrially according to this reaction. It is balanced. Okay. Then in a reaction, 1.5 kilogram of carbon was reacted with okay, so in a reaction, 1.5 kilograms of carbon was reacted with calcium oxide. Okay, this much of carbon was reacted with calcium oxide, and 2.42 kilograms of calcium carbide was produced. Okay, remember we want what percentage yield. So of what? Of calcium carbide. So it means the one that is produced. So it means we now know the mass of calcium carbide that is actual, that is calculated actually, or that was produced. It is 2.42 kilograms. which is the same as 2,42. Remember I said kilo, just say multiply by 10 to the power of 3 kilograms. Okay, let's just save this information for now. But now we need to calculate the mass of calcium carbide that did what? That the theoretical one. Okay. So remember there's three steps of what? Stoichiometry, and then the last step. So the first step, it is me using the one with the more information. Which one is that? It is the carbon. I'm told that 1,5 kilogram of carbon was reacted. Remember, if I have if I have mass of carbon, I can get its molar mass. So I can say number of moles of the known, it is my carbon. It is equal to mass divided by what? By molar mass. Okay, number of moles. Let me just say, indicate here. It is number of moles of what? Actually, okay. Number of moles of carbon dioxide. I think it's carbon. Okay, let me rewrite this. Number of moles of carbon, it is equal to mass divided by molar mass. The number of moles of what? What is mass of carbon? That was reacted. It is 1.5. Remember this 1.5, I'm going to convert it. This is the information that we use. This 1.5, I'm going to convert it to grams. It's going to be 1.5 multiplied by 10 to the power of 3 grams. Not kilograms here, grams rather. So it's going to be, you can use your calculator, 1.5 times 10 to the power of 3, which is the same as multiplying by 1000. Okay, I get something like 1.5 grams divided by what is molar mass of carbon? Molar mass of carbon, it is 12. The number of moles of carbon, or even if I were to write it here, okay, it's fine. Number of moles of carbon, just to remind myself, it is divided by 12. I get something like 125 what? Moles. Okay, then I'm going to need them what? Step 1 is complete of stoichiometry. Then step 2, it is use what? Molar ratio between the known and the unknown. The known, it is carbon. Then what is the unknown? The unknown, remember, I need to calculate calcium carbide. That is theoretical. So I will just want the mole of calcium carbide. Now, what is the ratio between, this is 3:1. 3:1. Mole ratio 3:1. And then what is the number of moles of carbon? 125x. Then when I do my mathematics there, you'll get that x, which is equal to number of moles of calcium carbide, theoretical. It is equal to 125 divided by 3. Divided by 3, something like 41.667, or let's say 41.67 what? Moles. Okay, then now that I know the number of moles of calcium carbide theoretical, I can get what? Mass of calcium carbide. Whereas where the molar mass of calcium carbide, it is what? Calcium, it is 42 multiplied by 12, then I get something like 64. Yeah, I get grams per mole. Then it's going to be number of moles of calcium carbide. It is 41.67. It is equal to what is mass? I do not know. What is molar mass? 64. Then what is the mass of calcium carbide? That is what? Theoretically. The one that we actually calculate is going to be 1.67 times 64. Then it gives me something like 2666.88 grams. Okay, then now I can say, for me to calculate percentage purity, percentage yield, sorry, I'm gonna need what? Mass of the actual mass, okay, as well as the theoretical mass. Even if you were to say actual yield divided by theoretical yield, is still the same. Then remember, I want the percentage, I multiply by 100. What is the actual yield? The actual yield we were given as 2,42 times 10 to the power of 3, which is the same as 242,000. Basically, what? Grams. 2,42 times 10 to the power of 3, it is I got 2440, sorry, 2420 actually grams. So I got 2420 grams. So the actual one, it is what? 2420 grams divided by what? What is theoretical? It is the one that you just calculated here, 2666. 26666,88, and then I multiply that by 100. Then I'm gonna get answer divided by 2666,88. Then you get something that is very beautiful, something like 90,74 percentage. So can you see this, how these examples actually work? So they actually work like this, and most of the time, and actually they always follow this same analogy thereof. Sometimes the examiner might be very genuine and be kind and guide you step by step. Okay, sometimes, but if it does not, just remember all the 4 steps. Okay, now can you see it is just 8 marks? How can they mark this? They can say 1 mark for this one, the ratio there for substituting here, they like that, maybe 1, 2, 3, 4, 5, 6, 7. I don't know how that other 8 came from. I don't know, maybe substituting the what, but whatever. Just getting your 8 marks there. Can you see how beautiful it is? Not only is it beautiful, it is also easy. Okay, yes. So now on the next video, we're gonna look at percentage compo. I'm not sure if, okay, my pen, I think my pen is getting tired. Composition. Okay, am I only one seeing this pen writing in a different way? But either way, it's fine. Percentage composition. And then after looking at percentage composition, not for a long time, we're going to look at what we refer to as empirical formula. Okay, yes. So on the next video, we're going to be looking at these two of empirical formula as well as percentage composition thereof. You need to know how to define what is a percentage empirical formula rather, and then you'll be in a position of knowing exactly how to calculate that. Okay, let me just confirm if the empirical formula is written correctly. Yes. Okay, actually it's going to be empirical formula as well as molecular formula. Okay, yes. So thank you very much for joining me on percentage purity as well as percentage yield video. Hope you enjoyed, and let's meet on the next one where we finish off things now. Okay, for the topic we've been doing a lot. Okay, yes. Thank you very much.